Hello. In our previous video on electricity and magnetism, we had discussed about the properties of conductors. In this video, we shall be discussing about electric dipole at this level. So this electric dipole. Then we'll follow it up with the dipole-dipole interaction, and then finally the multipole expansion. And if we could, we'll try and squeeze in the electrostatic shielding, and then we can proceed further with the other topics in the next upcoming video. Now, to begin with, the electric dipole as we know it from our electrostatic days that we have studied in our higher secondary physics. So the dipole usually given by this, there is a negative charge and a positive charge of equal magnitude, and they are separated by a very short distance. The direction is from the negative to the positive, that of the dipole moment, which is usually represented by the p vector, and not to be confused with the momentum in this case. This is the dipole moment, and the distance over here is d between them supposedly. And then we may consider a point P as a point P, and there we wish to obtain the net electric potential as well as the electric field intensity due to this charge distribution over that, not the charge distribution but the dipole itself. So here we have the distance or the position of the point P with respect to the negative charge as r, and then we have the other one, that is well, the d vector probably acts from or is the position of the positive charge with respect to the negative charge. The negative charge can be considered to be placed at the origin. So in that case, what we get is the point P now has a position vector of r minus d, as from the triangle law. So r minus d is the position vector of the point P with respect to the positive charge. And by the definition of potential, what we know is that the potential at this point will be VR, and that will be equal to kq, k being equal to 1 over 4 pi epsilon naught. And then we have this one as 1 over r minus d, modulus of that minus 1 over r for the negative charge, because it's a negative charge, so we'll have the potential to be negative as well. Now, because the distance of separation d is very, very small when compared to that of the position vector r that we have taken, it's mostly that's the case. So what we get from that is that we'll be taking the expansion of this r minus d term, that is the negative power of that, and that will be equal to r square minus 2 times of r dot d plus d square raised to the power minus half, and that will be equal to 1 over r, well, that can be taken as the common term, and then we have 1 minus 2r dot d, and that divided by r squared plus d squared over r squared. Now remember, what we said is that d is much less than r, so this term obviously can be neglected in this context. So we still have the minus half over here, and then this will be therefore nearly equal to 1 over r times of 1 plus, because the minus half got multiplied over there by binomial expansion that we know of. So this is r dot d over r squared. Now from this form we use this form over to the expression for potential. What we get is VR is therefore equal to k times of q r dot d, and that multiplied to r cube, because there's a 1 over r in that case outside. That gets multiplied when we take that inside that bracket in this term. 1 over r cancels out this 1 over r at the top, and 1 over r minus d, the rest of the term that remains, is this one multiplied to this. So we have r dot d over r cube. Okay, now in the limit that d tends to 0, means the the distance between the dipoles, between the given charges, that's really small, and that the charge extends nearly to infinity, that is for a point dipole. It is usually termed as an ideal dipole, and in that case the dipole moment remains constant, remains fixed. But the case of but that becomes an ideal dipole. Ideal cases usually are theoretical, they do not exist in reality. Real cases are much different, but still we can assume that. So now suppose that was just for the knowledge, that we consider the case of ideal dipole when those things happen, that is, the charge extends up to infinity while the distance goes to 0, but the product remains the same. So you have the dipole moment to be equal to q times of d. Now as far as the potential is concerned, with the knowledge that p is the dipole moment, we have kp dot with r, and that taken over r cube. Remember, the d has gone within that p, so q times of d has become p, and p dot r is what we have in that expression for the potential. And as you can see, the potential due to the dipole, there's an r vector at the top, and when we consider the unit vector, r vector over r is going to be r cap. So that can be written as p r hat divided by r square. That's another form of writing it, but it's the same thing. So as you can see, the potential here varies as the inverse square of the distance, and therefore it will fall more rapidly in case of a dipole rather than in case of a single isolated charge, because in case of a single isolated charge, as we know, we have already used that expression over here in this at the right at the top, kq divided by the distance. So in case of isolated charge, it's inversely proportional to the distance only, but here it is inversely proportional to the square of the distance, and that's what the effect of, that is what we see, the effect of dipole over the potential at a given point. Now with this information available to us, we can obtain the electric field from the relation that electric field intensity at a given point lying at a distance r is given by the negative gradient of the potential that we have just obtained, and that being equal to minus of k is a constant that can be taken outside, gradient of p dot r over r cube. This is what this one is, the thing that I have used. So this will be equal to minus of k, and as far as that gradient term is concerned, what we get is 1 over r cube, is a constant that can stay out. So this is gradient of p dot r plus p dot r, and then we take the other term, that is the 1 over r cube, and we keep p dot r as the constant term. As far as the first term is concerned, if you observe closely, is the gradient of p dot r, that is pxx, pyy, pzz, and the gradient operator, as you know, it is del over del x, that is the partial derivative with respect to x I hat, partial derivative of y j hat, partial derivative of z k hat. All of that is going to eventually end up as only the p vector, that is the dipole moment itself. And then as far as the gradient of the second term, that is 1 over r cube, is concerned, we have that to be equal to minus 3 1 over r raised to the power 4, but because it's a vector quantity now, so we can have an r cap, and instead of r cap we have r over r modulus. There was r to the power 4 after the derivative, and with that r cap available, we can write that as r vector over r. So another r gets multiplied in the denominator, so we have minus 3 r vector over r raised to the power 5. Now we use these in the expression for the electric field, and what we get is that the electric field intensity at a point r is given as k, when the minus can be taken inside now, and so the second term, which was the negative term, becomes plus. So this is 3p dot r over r raised to the power 5 r vector, and then we have minus of p over r cube, which was the first term in the previous case, becomes negative after that minus sign has been taken inside. And we can further simplify it as k over r cube, and the rest of the things are as such. With the r cube gone, the denominator term over here simply is r squared, and then the p vector remains for the second term only. And this equation that we have is it can be obtained from the direct application of the Coulomb's law that we have already used in our electrostatic portion. You may go through that. It'll be giving the same result over there. Now we wish to provide the expression of the field intensity along the different axes that we have. So if we were to take the direction of the dipole moment along the z-axis, let me draw another figure for you so that you'll be getting what the type of expression. We'll be extending it to different coordinate frames, coordinate systems, for which will help us to ease the calculation. So here's a representation of the same diagram as that in the top, but at the top you have the position of the point P from the origin, which is the same as over here that we have drawn as from the origin O to the point P there, and the electric field intensity in that case, it extends in that line, along that line, that is ER vector goes along that direction. Now we have two components of E vector, that is the ER vector, and that makes an angle theta with respect to the z-axis. Z-axis, Z being the axis, as I told, the dipole moment is now aligned along the z-axis. As you can see, there is a negative charge on the left hand side and the positive charge on the right hand side, and the dipole moment P extends along that z direction, and the point P is situated at an angle theta. We have the spherical coordinates on that plane, that is ER and E phi, and ER, as you know, is making an angle theta with respect to the z-axis as shown. So we wish to obtain these components of the electric field intensity, and we'll be using the expression as we have obtained over here to obtain those components. So if we first look at the case of EZ, now EZ in this case would be equal to at least when we see the magnitude of it, we say that Ez is equal to k over r cube, and when we put that z for that r vector that we see, so we have 3p z squared over r squared minus p. And if we observe closely, then we have z over r to be equal to the cosine theta in this case. So this is equal to k over r cube, and p can be taken outside one of the p, and we have 3 cosine squared theta minus 1. That's the value of z. What about ex? Ex is equal to k over r cube, and that is equal to 3p xz divided by r square, and x over r is sine theta, z over r is cos theta, so you have k over r cube, and there will be a p in that, okay, and 3 comes outside, so this is sine theta times of cosine theta. That's the expression for ex. Now, as far as the coordinate transformation is concerned, they are rotated through an angle theta, and from the expressions that we see over there for Ez and Ex, we'll use them to obtain those Er and E phi. If you look at the figure, Er cosine theta is acting along Ez, while Er sine theta is going to act along Ex. Then again, E phi, and because Er is making an angle theta with respect to Ez, similarly E phi is making an angle theta with respect to Ex. So E phi cosine theta is going to act along Ex, while E phi sine theta is going to act opposite to Ez. So what we have as the equations, let me write them in the next page while you consider this figure. Keep that in mind or draw it somewhere so that it can help you to observe or to know what I am writing over here. So in this case, what we get, so along Ez, that we have as the expression being kp over r cube 3 cosine squared theta minus 1, and along that Ez, what we find is that Er cosine theta acts along that direction, while E phi sine theta acts opposite to it. And as far as Ex is concerned, we have that expression as, if you remember, 3kp times of sine theta times of cosine theta over r cube, and that is equal to, as we saw, that the sine component of Er acts along that line. Also, the cosine component of E phi acts along that direction. Now, if we multiply a cosine theta at the in the first case, the first expression that is, and a sine theta in the second expression, and add them up, then what we find is the E phi terms, they become equal and opposite, and they cancel out each other, while Er with a cosine theta multiplied Er cosine squared theta, Er sine squared theta at the bottom, we add them up and we find only Er. So Er is going to be equal to, since we have added cosine theta for the expression at the top, similarly the cosine theta gets multiplied onto the left hand side as well. So we have kp over r cube, and we have 3 cosine cube theta, probably we'll keep it to cosine squared theta multiplied to cosine theta minus cosine theta multiplied, that was multiplied to 1. And then the other term that was multiplied with sine theta, we have 3 kp divided by r cube, and then we have sine squared theta times of cosine theta, and that's the only term. So finally what we get for ER is that from this we get ER to be equal to, so 3 cosine squared theta kp by r cube, sine squared theta kp by r cube, and there's a 3 factor over there as well. So they get added with the cosine theta as the common term as well. So we have, what are the common terms? So the common terms are 3 kp divided by r cube cosine theta, and the rest of the term, that is cos square theta plus sine square theta, goes to 1. And as far as the second term is concerned, there's a minus cos theta left out, so we keep that as such. So minus cosine theta remains as such. We can take that as common as well, so there's no big deal with it. So cosine theta can be taken as common term. And as you can see, this kp over r cube will be multiplied to this cosine theta as well. So we have a kp over r cube in this as well. So 3 kp minus the kp term gives us 2 kp over r cube times of cosine theta. That is what we get for ER. What about E phi? Well, E phi is just the other way around. In the first case, for obtaining ER, we had multiplied cosine theta at the top expression, and the next expression was multiplied with sine theta. We go the other way around this time. We multiply a sine theta at the top and a minus sine theta, because there's a minus sign over there. So minus sine theta, this one, equation 1, equation 2, what we do is, for this, equation 1 was multiplied with cosine theta, plus equation 2 was multiplied with sine theta. So the result was this. Now equation 1 is multiplied with a sine theta, a negative of sine theta, and then equation 2 is multiplied with cosine theta, and they are added. So what do we get? We get, in the first expression, let's take the left hand side first. In the left hand side we have kp over r cube, and then we have minus 3 cosine squared theta plus sine theta, because that was what was multiplied to it, and plus, in the next case, we have 3 kp over r cube, and there was a cosine theta multiplied to it, so sine theta into cosine squared theta. I hope I'm doing it correctly. And on the right hand side, what you see is ER cosine theta minus sine theta, and ER sine theta plus cosine theta. So ER terms cancel out, and we are left with E phi on the right hand side. So that gives the final expression for E phi as E phi is equal to, so you have 3 kp over r cube and a 3 kp over r cube in the denominator as well. So, and we have a cosine squared term in common to both of them. I've probably missed out on the sine theta over here, so there was a minus sine theta multiplied. I wrote the minus sign but forgot the sine theta. So cosine squared theta and sine theta minus 3 kp over r cube plus 3 kp over r cube, they cancel out completely. And what we are left with is only the second term multiplied to this, that is kp over r cube times of sine theta. That's the only term that is left, and that is the expression for E phi. And with all these expressions and with all these components that we have for the electric field intensity, it is easier to determine and use them in a few cases, in a few problems, as you would be seeing. We'll be doing a few numerical problems on this as well, and these come really handy. They are really effective in calculating certain values. These can be obtained easily by using the expression, the general expression at the higher secondary level that we have studied. But these expressions in the polar spherical polar system, they are a lot of help in the kind of calculations that we are about to follow. We are pretty aware of the expression for the dipole, or the behavior of the dipole when placed in an external field. Usually it is the uniform field that we are talking about. So in the external uniform field, the dipole is acted upon by an external torque that arises due to the coupling forces offered by the external field on the positive and the negative charges. And so the expression for the torque is equal to P cross E. E is that external electric field that acts on the dipole, and if it is twisted through a certain angle, there is some work done by the torque, and if we wish to align it in some with some orientation, then we do some work on it. Supposedly we wish to twist it through a certain angle theta, then we do the work, and that work is stored in the form of the potential energy within the dipole, and that potential energy is given by minus of P dot E. So it's the dot product of P and E. In case the E is obviously the external electric field, uniform electric field acting on the dipole. So this is the expression for the potential energy stored, or even the work done on the dipole in the presence of an external field, as well as the torque that is acted upon the dipole by an external field. We are not going into the details of it because they have already been derived in one of my previous videos, so I'm not really going to do them in detail. I'll be providing you with the links later, or you can check for yourself. Then we will move over to the case of dipole-dipole interaction. How two dipoles, if in the nearby region, how they will be interacting with one another. That is what we are about to find out. Now in this case we shall consider the potential energy of one of the dipole placed in the field of another dipole, right? So in order to obtain the potential energy due to this dipole-dipole interaction, what we use the expression for work that we just obtained over here, or just wrote over here. So the expression for work, that is, let's say the second dipole has a dipole moment P2 and the field of the first dipole is E. So the potential energy of that in that case would be minus of P2 dot E, the same expression that we have over there at the right hand side. And we just put the expression for E due to the first dipole. The first dipole probably has a dipole moment P1, and we have an expression for that. We have an expression over here, right over here in the previous page, if you remember. There at the in this line over here. Yes, so 3p dot r vector over r squared minus p vector, and k over r cube is always there. So we have in that expression, what we can do is we put a minus p2 as it is, and then the dot product with k over r cube, which remains as such, and then we have the expression within the brackets, that is, what was that? That was 3p dot r vector over r squared, 3p dot r times of r vector over r squared, and this is p1 because we are considering the first dipole, and then minus p1 instead of the only p that we wrote over there. This is p1, Now with the dot product, we have this as k over r cube 3, and this is p1 dot r times of p2 dot r over r squared times of, well, we can keep the r cube aside, and this is negative. And then the second term is simply p1 dot p2. Now if you were to consider the condition that I'm going to draw over here, that we have a dipole, supposedly we have two dipoles of equal dipole moments, then, and they are separated through a distance r, s probably. So this is the first dipole with the negative and the positive charge over here, and it has a dipole moment, say p, and then we have another dipole which is probably separated from the first one. Again, we have the negative and the positive charges, and this has a dipole moment p as well, and the distance of separation between them, in this case, either we take from the first negative to the second negative, or from the first positive to the second positive, taken the former case, so let that distance be s in this case. So over here what we are going to see is that we are going to use that expression that we obtained for the potential energy, or probably the work done, that we have obtained over here. So what is that expression? How does that expression come? In this case, I'm not changing the ink over here, I'm keeping it the same. So this is minus of, we can take the minus, there was a minus sign over here, this has become plus. So this is k over r cube, and because the p dot r and p dot r in this case is simply s, so instead of r we have s cube over there, and in that expression within that bracket we have a minus of 3 p1 p2, they are the same, p squared, and the dot product is s squared divided by s squared, gets cancelled out, and then we have p squared over here. So this is negative of 2 times of k p squared over s cube. So that's the expression for the potential energy, or the work done. It's usually the potential energy. The potential energy due to the mutual interaction of the dipoles that has been given by this figure. This is along the side-on position, end-on position. There will be different expressions if we use the values for different angles. So this is this is the interaction between the dipoles and the energy that is involved between them. In the next case, we are going to discuss about the multipole expansion of the electrostatic potential. In this case, we are considering a volume charge distribution where a charge, supposedly Q, a certain given amount of charge Q is distributed over a volume V, such that you have the volume charge density as rho, and as far as a small volume dV considered in it, which has a position vector r primed as seen in the figure with respect to the chosen origin of a coordinate system, rho r prime is the density, is the volume charge density, and if we are to consider the volume dV, then it will have a small amount of charge dQ, which has the corresponding value rho dV. So dV times of that is giving me rho r primed times of dV primed, because we have considered the primed volume in that case, and we wish to determine the potential at a point P where the position of the point P is much larger, or is at a greater distance, that is r vector here is much greater than this r primed vector. That's the position with respect to the origin chosen. And the position of the point P with respect to the given volume is obviously r minus r primed as per following the triangle law. And the expression for the potential in this case would be VR. This is the potential for the at the point P due to the given small volume, and for that entire volume considered, this will be integrated over the entire volume now, and we'll have rho r prime. This is the dq amount of charge in that given volume dv primed over, so this is kq over r in this case is the distance over here, that is r minus r primed in magnitude. Now the expansion of the denominator is necessary because we have the, as I said, we have the condition over here that r is much greater than r prime, so we have r minus r primed taken inverse as this expression, that is the same thing that we had done previously while considering the dipole moment, and obtained the expression for potential in the beginning of this video. So r primed squared, and that raised to the power, entirely raised to the power minus half 1 over r. Will be extending not only to the second term but probably to the third term as well, so that we can expand it to much higher terms, and we'll be getting according results. I'll tell you what kind of results are we expecting from this kind of an expansion. So this is as per the binomial expansion that we know of. This is the second term of that binomial expansion, and the third term that follows is half times of half over 3 over 2, and it is multiplied to the terms minus 2r times of r primed. This is r primed over here as well, then that divided by r squared plus r prime squared over r squared, and this is squared entirely, and then we have other terms in the expansion as well. Now we use this value, that is r minus r primed inverse of that, we use this over here, and what we get from that is that VR is going to be equal to k times of that volume integration term, and we will be keeping these terms that we have for 1 over r minus r prime. So 1 over r first, this goes in, multiplies to the other terms that are present over there. In the second case we have plus of, because minus over there is plus of, that is r dot product with r primed divided by r cube, and then we have for the third term we can take a few common things, that is half of 3 r times of r primed, and that is squared divided by r raised to the power 5 minus r prime squared over r cube plus the rest of the terms, and all of that multiplied to rho r primed, rho of r primed dv primed. Now as this r vector, it is independent of the variable of integration, that is r primed, so that can be taken outside of the integration, and so we have a VR over here to be equal to, we take the r value out of the integration, so we have the k over here, and we keep 1 over r out of that integration, so we have this over entire volume, rho r primed dv primed. That's for the first term, and as far as the second term is concerned, we have r over r cube that goes out, and then we have v r primed rho r primed dv primed, then plus, we'll make it much easier with a shorthand notation that I'm going to use later. We'll be having three values extending from 1 to 3, uh, and we will be taking the components. So xi and xj here, they simply represent x1, x2 and x3. As you can see, the summation is from 1 right up to 3, x1 being equal to x, x2 being equal to y, and x3 being equal to j in that case. And we introduce the case of the Kronecker delta term, that is in the first term we'll keep it as such, that is xi primed and xj primed, and in the second case we have the Kronecker delta of ij r prime squared, all of that again multiplied to the rho r primed dv primed factor, k multiplied with each of them. So as I said that xi and xj, xi primed and xj primed, they are the Cartesian components of the r vector and r primed vector. As I said, I stands for x1, x2, x3. Same goes the case with j, and x1 being equal to x, x2 being equal to y, and x3 being equal to z. So they are the Cartesian components. Now as far as the Kronecker delta is concerned, you may be knowing this, that delta ij is equal to 0 when I is not equal to j, and delta ij is simply equal to 1 when we have I to be equal to j. So the first term on the right hand side of the above equation that we see is the electrostatic potential of the total charge if that were concentrated right at the center. So this is the expression for the charge to have been concentrated at the center. Then we would have had the potential energy term or the potential term as this. The second term in the potential that we have, if we are comparing it with the expression, the usual expression for the potential, what we get is that this factor over here represents the dipole moment, because there's a charge over here and there's a distance over here, so that represents the dipole moment, which is when it is located at the origin of the coordinates. And then we have this as the dipole moment of the charge distribution. And as far as the last term is concerned, we have this value, the third term, that is, so let me rewrite that for you. So we have k, that's over here, it's multiplied over here, and then we have the two summations. We'll drop the i's and the j's over here, repeated writing of that. Then we have xi xj over r raised to the power 5, and then we have a factor qij, where obviously, as you can figure out, qij is simply that integral term, that is integration over the entire volume, 3xi primed xj primed minus the Kronecker delta ij r primed square, and all of that multiplied to rho r primed, rho of r primed dv primed. Now this qj factor that you see over here, as for I and j taking up the values of 1, 2, 3, you have 9 components of qij, therefore, with the i's and the j's taking different value. I taking 1, then j taking 1, 2, 3, I2, j taking 1, 2, 3, and I3, j taking 1, 2, 3 values. So you have in all 9 components, and you can see there are two sets of there are actually 6 pairs in them, and therefore we have 6 distinct components in this case. This set of quantities constitute the quadrupole moment tensor. So this is what we call as the quadrupole moment tensor, right? And it is an extension of the dipole moment concept. The potential due to a dipole, as we have observed, it drops off as 1 over r squared. And if we observe over here with xi, xj at the top and r raised to the power 5 at the bottom, the quadrupole moment that drops off as 1 over r cube, which means it reduces rapidly. And the dipole moment has the unit of coulomb meter in that case, whereas the quadrupole moment will have a unit of therefore coulomb meter squared. Not the tensor but the quadrupole moment as a whole. And if we retain the much higher terms that we have excluded in this expansion, we have just left them out, then we'll be obtaining higher order moments corresponding to higher order multipoles, right, which is an important which is of much importance in nuclear physics. And so this is the case about electric multipoles. The electrostatic potential due to a charge distribution can be approximated by using the case of electric multipoles, and extremely complicated problems, they can be solved by taking such approximations. They take the case of simple cases like water and carbon dioxide molecules. In water, it has a net dipole moment because the oxygen atom, they carry a net negative charge, and each of the hydrogen atoms, they always carry the net positive charge. So with 2OH being aligned at 104 degrees approximately, the dipole moment of the molecule is the resultant of the dipole moments of the two OH bonds that we have. And this dipole moment is quite strong and accounts for some characteristic properties of water. Also, in case of carbon dioxide, it has a linear symmetry. You have carbon in between, and that is sandwiched between two oxygens and oxygen atoms on either side. So you have two dipoles, and both those dipoles are actually directed in the opposite sense. So in that case, you will have this, and this, and the dipole in that case is completely equal and opposite, and that is why the dipoles, they cancel out each other. So there's no net dipole moment in case of the carbon dioxide molecule. However, as we will be observing in one of the numericals that we'll be doing later, that it has a quadrupole potential which varies as 1 over r cube. That is what we have just mentioned. So that is all we were to discuss. We'll be discussing the electrostatic shielding in the next video, and then we'll follow it up with some worked out problems. Electrostatic shielding is pretty easy to know. I think I can spare 2 minutes to just explain that to you in this video itself. So what we have over here is that we try to produce a region in space where the electric field is 0. So we literally shield that space from the external electric field. So that is electrostatic shielding. Such field-free regions are of experimental importance, and because they are, we can place devices which should be kept away from the external electric field. So what we do essentially is that we consider an empty cavity inside a conductor, just as in the figure that I've shown over here, and the potential inside this cavity, if the potential of the conductor is supposedly say V, the potential inside the cavity is going to be V, because the electric field is 0, so the potential remains constant, and there's no charge over there, so the potential everywhere inside the conductor is the same. And even if there may be an external field outside the conductor, it won't really impact it. So if we place probably a charge or a substance within that cavity over here, and it is shielded from the external field, because the external field will cause the outside field is also protected from this internal field that may develop when we place a charged body. So let's assume in the first place that we have a charged body inside the cavity, and consider probably a Gaussian surface which is enclosing that cavity. So we consider a Gaussian surface over here, and it encloses that cavity over there. And since the electric field is always going to be zero everywhere inside the conductor, so what we have is that from the Gauss law, or from the case of conductors that we have studied the properties related to the conductors, the electric field inside the conductor is always going to zero, always going to be zero. So the net charge that must be enclosed by the surface, that has to be zero. So in that case, what happens that if we have a charged object over here, let's say it has a positive charge, an opposite charge must be induced in the inner surface of the given conductor. So in that case, if we are placing a positive charge over here, the inner surface of the conductor, I hope that is visible, I'll use another ink to show you. So this is the inner surface of the conductor that I'm showing you. So that inner surface now carries an equal amount of negative charge distributed in its inner ring, so that the net charge that is enclosed by that Gaussian surface, that goes to zero, because the field must be absent. It needs to be absent within the conductor. So in that case, what we get is the negative charge that was built up over here, because this is a conductor and probably the conductor was electrically neutral, with the accumulation of the negative ions on that inner wall, the positive ions start to appear on the outer wall over here. And as you know that the total amount of charge that has started accumulating on the inner wall over there is making that stuff electrically neutral, that point or that Gaussian surface region enclosed by the Gaussian surface, that being neutral, which means that negative charge is equal to the amount of positive charge that was there. So the positive charge that has appeared is equal to the positive charge that is placed inside that cavity that we have placed. So that charge that we placed inside has appeared outside now. But if we wish to protect the external region from the field due to this charge, what we do is simply we ground this. Now if we have grounded this, then both the inside is protected from an external field and the outside is protected from that internal field. And that is how we carry about this process of electrostatic shielding. So that's more or less the things that I was about to discuss in this video, as I had mentioned right from the beginning. And having finished that, we have completed this portion on electricity and magnetism. We'll be trying out a few problems, a few examples related to the topic that we discussed, and then we'll be moving over to the next topic in the upcoming videos as well. Till then, thank you for watching.